it's never too late to subscribe to our mailing list, so you can send the word webinar to our email or to our WhatsApp number, which you'll find on the chat, as well as the links to our calendar, which is just now kind of moot, and our previously recorded talks on our YouTube channel. Do not feel compelled to subscribe or click the little bell or anything. We don't care. We just want you to watch any of the great talks we've had this year, if you want. This is the season finale. This is the last seminar of 2020. In South America, we're about to go into the summer. So we don't yet have a schedule for 2021, but there'll definitely be one. So stay tuned and do subscribe if you want to be informed about that. Today, we're going to have Simon Salomon, one of the founding fathers of what we now call sort of special geometries. It's become a large field, but back when it was it's mostly Bush, he's the one who helped shape the kind of questions we'd be asking for the following decades. On a personal note, he taught me a great deal during my own PhD. He's probably the most influential figure in my choice of G2 geometry and gauge theory back then. And so I'm very happy to have him here at our seminar to conclude this year. So Professor Salomon, very welcome. Please go ahead, tell us about Lie groups in special.
Okay, thank you, Henrik. Sorry, unfortunately I started presenting before I've checked my own camera. You can see me, can you? Am I sort of more or less in the middle of the screen? Do I need to adjust anything?
User experience is pristine.
Okay, very good. So I've forgotten the abstract I wrote for this talk. However, the plan is to sort of talk around Lie groups and give some examples of special holonomy, explain some recent work by other people and also myself, time permitting, in this direction. But I want to give lots of sort of examples. Now, I know there are many experts watching, and this will be very well known to some of you, so please bear with me. But I think there are some, I just want to introduce things in perhaps a slightly different way from usual. And the emphasis is on giving explicit examples, which of course was the way I was introduced really to G2 and spin 7 holonomy by finding explicit metrics about the time working with Robert Brown, about just after he'd done his more abstract existence theory. So I want to start with the sort of list that Berger gave in the many years ago of possible holonomy groups of Riemannian manifolds. Of course, assuming that it's not symmetric, that corresponds to Cartan's classification. For simplicity, let's suppose it's simply connected, but that's just technical. It's not essential. Just that I'm talking about the standard holonomy group. And so there's this list of groups. Now, at the time he did the list, apart from a few of them, it wasn't known whether the corresponding metrics existed. In fact, there were a couple of other groups on the list. Spin 9, which in fact we now know can only occur for symmetric space, and there was SPN U1, it's often forgotten. But this is effectively his list. And today I just want to give an explicit example of a hyperkalemetric in 4 dimensions. So can you see the cursor, by the way, or not?
Yes.
Yes, so I can annotate if I need to, but in 4 dimensions, that would also be SU2, so that should be in red as well. So I want to give an explicit example of actually a fairly well-known metric, which is hyperkalar in 4 dimensions, but explicit, and the same for G2. So that's why I put these 2 in red. I won't really talk about the other groups here, but that's the classification of holonomic groups. And you know, here we're talking about groups acting at a point on a manifold, sort of gauge groups, structure groups acting at each point. But I want to talk about the use of Lie groups more widely as sort of isometry groups and as settings for the ambient manifold. Okay, and an example I know is very, very familiar to many of you, particularly in South America, is I want to talk quite a bit about nilpotent Lie groups. I won't be talking about solvable Lie groups that are not nilpotent today. So the sort of easiest thing to start with is the Heisenberg group. So you can think of this as the group of matrices or triples in which the multiplication is given by this formula. It's a sort of simplest thing that's not the 3 torus. It's not quite abelian because of what's going on here. And you immediately see from this multiplication that it's a Lie group, so it's parallelizable, and it has this basis of left invariant 1 forms in these coordinates. So, you know, if you do group theory, you try and draw the Cayley graph of groups. And I found this is a screenshot from someone's YouTube video. It's a bit of a joke because they're using grapes. I think grape is the name of some geometric software or something. But the fact that this isn't a nice sort of rectangular lattice is measuring the fact is it's not abelian. But what you do see is that if you do the commutator in the sense of group theory, you immediately get the first 2 coordinates 0. So you get something that lies in the center of this Lie group. And that's telling you that, of course, if you do more commutators, you'll get the identity, which is 0, 0, 0. So this is telling you that, obviously, as we all know, H is a 2-step nilpotent Lie group. And of course, to get the manifolds, to get the compact manifolds, we want to choose a lattice. So we can take, for example, X, Y, and Z to be integers. And then we can divide out by that acting on the left. So you can think of A, B, and C as being integers. And we get the very simple example of a nil manifold, the quotient of a nilpotent Lie group by a co-compact discrete subgroup. So that's basically the setting for the defining a 4 manifold, which is just going to be this 3-dimensional nil manifold I've just told you about, the Heisenberg group over a discrete subgroup. And we're just going to cross that with a circle. So you could think of the whole thing as the quotient of a 4-dimensional group, the nilpotent Lie group. And of course, 4 manifolds is a bit more geometrical structure we can start to define. And, you know, this is the way you do things. It's very easy if you want to get into sort of elementary differential geometry, you know, it's fantastic examples, these nil manifolds. So here we've got a basis of 1 forms. All I've done is added on a 4th one. You should see this amendment by hand here. E4 is dt coming from the S1, t being the angle, and S1. And of course, we know that, I mean, the Lie algebra, by the way, when I talk about Lie algebras, you can think of that as just coming from the exterior derivative acting on 1 forms. So these equations here define the Lie algebra, the underlying Lie algebra. And it's almost abelian, but we have d of E3 is minus E1 wedge E2, which is obvious from this formula. And I'm using this abbreviation, so wedge products are just denoted like this. I use that in my lecture today. And then it's obvious, perhaps I'm going ahead of myself, it's obvious that the you can, obvious, not quite obvious, but one knows one can compute the cohomology of these things by just using the invariant differential forms. So, you know, this is the classic example of, well, it's a manifold with odd first Betti number, so it can't be a Kähler manifold. Now, when I say the Kadara surface, that's a complex surface. I haven't yet told you what the complex structure is. So how do you get the complex structure? Well, again, we have this sort of basis of 1 forms. I define the standard Riemannian metric that makes these orthonormal. That gives me a sort of standard basis of self-dual 2 forms, which I've called omega 1, omega 2, omega 3. If you recall the definition of the exterior derivative, we know that everything is closed apart from E3, but d of E3 is E1 wedge E2. So omega 2 and omega 3 are closed 2 forms. If we consider on the other hand, the almost complex structure defined by the metric and omega 1, so that would just be the almost complex structure mapping a tangent vector E1 to E2 and E3 to E4, then that has as its space of 1, 0 forms at any point this spanned by these two, and it follows from the fact that these forms here are closed that this is a closed complex 2-0 form, and that will imply that in fact J1 is integrable in the sense that its near has tensor is 0. So we know that the first complex structure, almost complex structure, is actually integrable, whereas these two will not be. So when I say Kadara surface, I mean the manifold I defined, the compact form manifold I defined with this complex structure. That is the Kadara surface. But I already want to point out a feature of nil manifolds. Of course, saying the near has tensor is 0, that's just a sort of algebraic condition, and it's a deep theorem that tells you you've got holomorphic coordinates, that it's actually a complex manifold. But for nil manifolds, at least for this example, it's all sort of elementary, because you can actually write down complex coordinates for J1 by just fiddling around. And obviously x plus I y is a holomorphic coordinate in the sense its derivative is a 1-0 form. It's this 1-0 form. D of z, it's not quite true, z plus it, that's not quite obvious, but you fiddle around a bit, you add this term here and you get that the d of this to be a 1-0 form as well. So sort of integrability is elementary. Everything becomes polynomial with nil manifolds. So it's a very, I'm sure you all know this, many people know this, but it's helps you understand these sort of almost Hermitian geometry. So here we have an example which of course has both symplectic structures. It has a whole circle of them actually. It has a complex structure, but you can't put them together compatibly, so it has no Kähler structure. So let me pursue this a bit with this picture here. So now think of K. K could be the Kadara surface, or more generally, so parallelizable form manifold, in which we have therefore a global basis of self-dual 2 forms called omega 1, omega 2, omega 3. And you can ask, is each one, we fixed the metrics, these are compatible. So each one defines an almost complex structure. We can ask, is that almost complex structure integrable? Is the 2 form closed? And we've just done the example, let's see if I can write now. We've just done the example where we've got 2 closed forms, actually I call them omega 2 and omega 3. And that implies actually that the other one, the cross product, if you like, is complex. So in fact, we have a whole circle of symplectic forms corresponding to the equator of this 2 sphere, but the omega 3 in this case will be a complex structure. And that's what happens for the Kadara surface. But you can have other situations where you've got two of these that are complex, and that will imply the third one, the cross product, if you like, is complex. Or if one is complex and one is symplectic, then the third one has to be symplectic. That's a lemma. So that sort of singles out for you the well-known geometries. You can have all three complex structures, in which case the whole 2 sphere will be a 2 sphere of complex structures. That's the situation of hypercomplex form manifold. Or you could have the situation we've just done, in which we have a holomorphic symplectic structure, complex manifold with a holomorphic symplectic form. Or we can have both of these together, in which case everything works. That all 3 are symplectic, all 3 are complex. And that, of course, is a Hyperkalemetric manifold. All the tensors are parallel. Parallel means the holonomy reduces. I didn't define holonomy today, but if you don't know what it is, then it means you have parallel tensors. So if all these omegas are parallel, that means the holonomy will preserve the will reduce to the stabilized of all these 3 forms, which is SP1 or SU2. Now that's all pretty elementary, but it gets a little less elementary when you consider other conditions, which I'm not going to do today. But of course, if it's hypercomplex or hyperkähler, which is stronger, then of course the half of the Wahl tensor has to vanish. So you can look more generally and for manifolds which are half flat or anti-self-dual half flat, and you can find these on solvable Lie groups. There's also a situation in which you can have 2 complex structures, but the thing is not hypercomplex. And I don't know if there are any examples on groups, actually. That may be an open question. And then there are also bark flat. Bark flat generalized conformally half flat or conformally Einstein would be bark flat, but there are non-trivial bark flat examples on solvable Lie groups. And the search for sort of bark flat metrics on 4 manifolds is still very open. Okay, that's sort of chatting around. How much time have I wasted now? Okay, you're still with me, are you?
We're here.
Yes.
And
Okay, good.
35 minutes to go still.
Yeah. Okay. Well, I may need to sort of skip through some slides very quickly. But the point of what I've just been saying is that I introduced the Kadara metric, the Kadara manifold, and I'm now going to make it less elementary, get a sort of less trivial, not a left invariant, a less trivial metric by simply replacing the circle by a half line. So I can now use this function t as a global function, which I couldn't really do before. So I've got this function t. I'm now going to use t as a function, and I'm going to do more or less exactly what I did before. I'm going to keep omega 2 and omega 3 exactly as they were before, but I'm going to modify omega 1 by using this function t. So I take a function yet to be determined of t, which corresponds to sort of rescaling my orthonormal basis in this way. If provided I put the reciprocals here, then it's still the case that these omegas are orthonormal in this sense, and therefore I can now actually solve. I can in this case I can actually make omega 1 closed. Of course, omega 2 and omega 3 are already closed. So I can make omega 1 closed, and from what I said before, that will give me a hyperkähler structure because all the forms will be closed, and therefore they're all complex from my little tabular lemma before. So you can do that by elementary solving an ordinary differential equation, and it's very elementary, and you see that this function is roughly t to the quarter. And so you get this metric here in terms of the coordinates I introduced before. And this is a hyperkalemetric. Okay, and there are many ways to view this hyperkalemetric. It can be viewed via the Gibbons-Hawking construction, if you know what that is. That's when you have a hyperkalemetric with an S1 symmetry. The S1 in this case is coming, I guess, from the center, from this connection 1 form. Or you can consider it as a sort of kalemetric on a holomorphic line bundle over the T2 bit, which you can think of as an elliptic curve, and that sort of Calabi constructed these hyperkalemetrics by writing down potentials. So that's my first example of an explicit, if you like, it's my favorite metric, hyperkalemetric, explicitly written down. Of course, the coordinates are all very explicit. You could put this on a computer and check that it's Ricci flat, as these metrics have to be. But I just want to point out that this is my introduction to you, if you like to read this paper by Hein, Sun, Wieklowski, and Zhang, who actually used this as a little component, a little bit of their construction of hyperkalemetrics on K3 surfaces and showing how these degenerate.
So, Salomon?
Yeah.
So this metric it's non-complete, right? Because
no, it's not complete. It's sort of half complete. It's complete in. I mean, I put it's on this. That's right. No, it's not complete. It's not complete.
Okay.
It's
okay,
so yeah. So sorry, where am I? Going the wrong way. Okay, so that's the end of part 1, if you like. But I'm staying with nil manifolds for the moment. I'm staying with nil manifolds, and I want to now move up to 6 dimensions.
Simon, before you do that, because
Yes.
this example is so neat,
Yes.
maybe you can explain the heuristics behind it. So how did you? We believe this is the solution, but how did you figure the trick was to use f squared and
Well,
f
the trick is, I mean, probably underlying this is some sort of structure on the 3 manifold that you can evolve some sort of geometrical structure on the 3 manifold and construct a metric with holonomy SU2 if you evolve it in the right way. But I mean, I tried to say it as I would naturally do it. That is, you already had 2 closed two forms. You want to get the first one closed, so you think you might put function of t here and a function of t here, but if you want to get it to be the algebraic conditions to be satisfied for omega 1, omega 2, and omega 3, you need to take the reciprocal, that whatever you put here has to be the reciprocal of this. At this point, you've only got one function, and you know, and then there's not much to check. You just have to write down the equation that d omega 1 is 0, and this is what you get. Okay.
Excellent, thanks.
I mean, but I mean that was my way of explaining it. But if you know about Gibbons-Hawking, then you can write down some harmonic function on T2 cross an interval, and so on. You know, there are different ways of seeing this. I mean, I ought to say this is a very simplified account. I mean, you can also change the manifold, you can change the lattice, and take different variants. You know, you can change the parameters in the lattice and get whole families of these metrics.
Perfect, thanks.
Okay. So in 6 dimensions, you know, so the message is that these nil manifolds, they're very good for, so I don't know which way to move. These nil manifolds are very useful. I mean, this example shows they're very useful. Now, in 6 dimensions, things get much sort of more interesting in terms of the possible nil manifolds you can construct. So whereas in 4 dimensions, we basically only have 3 examples, of which only one really is interesting. In dimension 6, so the nilpotent Lie groups would correspond to nilpotent Lie algebras, and there were 34 isomorphism classes of those. So each of those will give, even without worrying about the choice of lattice, we'll have 34 sort of different, very distinct nil manifolds. And in terms of geometrical structures, so here there are sort of 4 different classifications. So first of all, you have to classify nilpotent Lie algebras in dimension 6. That was done maybe 40 years ago. Then you have to classify the ones that have a symplectic structure. Well, that's fairly easy because you're just looking for closed forms, and that was done maybe 30 years ago, maybe by people in France. And then you have to find which ones may admit a complex structure, left invariant. I'm always talking about left invariant structures. And that was done by me about 20 years ago. And then you can try and ask for the G2 holonomy, which I'm about to talk about. And so I want to do the same trick of evolving a structure to get a metric, an incomplete metric with holonomy G2. And to do that, you need to start with the so-called half-flat SU3 structure. And these were classified by Diego Conte, who I think may be listening about 10 years or more ago. So putting all these things together, I'm particularly interested in the symplectic ones, the ones that admit a symplectic form, the ones that admit a complex structure. Of course, they can't admit both unless they're torus, unless it's abelian, because none of these things are scalar, or whether they admit a half-flat structure, which is represented by the blue circle here. So, you know, there are various ones. There should be, these numbers should add up to 34. There are 2 very nasty ones which don't fit into any of these 3 categories. Not sure whether they have interesting geometry. But, you know, for example, this one here, which is sort of, so this is in the intersection of half-flat and complex, but not symplectic. That should correspond, if I've got this right, to this example here. So this is the sort of code for saying this is the Lie algebra, in the sense that I'm telling what the exterior derivative does. You don't need coefficients. All the coefficients are either 0, 1, or -1. And this is saying that D of E4 is E1 where G2, D of E5 is E2 where G3, and so on. So we have this classification and we can do things, but by far the most sort of useful nil manifold in 6 dimensions that sort of fits into all categories is the complex Heisenberg group, which is given by this one here. And when I say white, this is meant to be white in the middle, but I've got my colors, you know, maybe my primary and my secondary colors mixed up, but this is somewhere here. So it's everything, you know, the complex Heisenberg, or the so-called Iwasawa manifold, which it produces. We're more interested in the underlying real manifold, underlying real geometrical structures. This can be used as a counterexample or constructing examples of all sorts of structures. So this is going to be the example I'm going to use next. So we use this complex Iwasawa manifold. I was going to use that in just 1 minute, just go quickly through here. So I was saying half-flat structures. So I haven't given you the definition. The definition is here. An SU3 structure, which therefore consists of a two-form, well, let's say a metric as well, a compatible Hermitian metric, and we're reducing to SU3, so a complex volume form. So this is half-flat if, say, the real part of the volume form is closed. You can rotate by circle, and the real part can be what you want, but one of these three forms is closed, and the square omega wedge omega is closed. So omega wedge d omega, the so-called co-symplectic condition, holds. So this is Simon Kiosi and I introduced this notion, but it was basically dovetailed with the sort of evolution equations that are sometimes called the Hippian evolution equations, although I think they were known long before. So you can, if you have one of these half-flat structures, and it's called half-flat because the intrinsic torsion, half of the intrinsic torsion vanishes. Instead of 42 components, you have 21 components. If you have one of these half-flat structures, that they are the structures you get on a hypersurface in a manifold with holonomy G2, because you have a closed 3 form and a closed 4 form, which are these, when you pull them back, you get psi plus and omega squared. So conversely, if you have a sort of real analytic half-flat SU3 structure, you can evolve it and get a metric with holonomy G2 on the product of that manifold with some interval by solving these evolution equations. And the sort of standard example of this, very special example, is if the manifold is what's called nearly Kähler, which means almost all the torsion is 0. Instead of 21 components, you just have 1 component. And it means the intrinsic torsion is invariant by SU3. In that case, it's really nearly Calabi-Yau in the sense these formally behave very much like Calabi-Yau manifolds, but they're Einstein rather than, they don't have 0 scalar curvature. Then, of course, it's well known that if you do the evolution, you get the conical metric. So the cone over a nearly Kähler 6 manifold has a metric with holonomy G2, as is well known. But I'm going to give another example. I'm going to start with the nil manifold I talked about. So it'll be more complicated. It won't be nearly Kähler, but the metric you get is much simpler in some sense. So this is the analogous example to the Hyperkalemetric 4-dimensional metric, which I mentioned. And there are a whole crowd. Of course, I told you how many half-flat, I've forgotten myself, but there are lots of half-flat 6-dimensional nil manifolds. This is just one of them. You can imagine you can get lots of metrics with holonomy G2, but they're all going to be incomplete. And here's perhaps the simplest one that I think already Simon Kiosi and I wrote down, but I studied further with Vestislav Apostolov and Diego. So it's based on the Iwasawa manifold, which is just the same, just completely analogous. I've just taken the complex Heisenberg group. I've just x, y, and z now are complex numbers, and you factor out by the Gaussian integers. So you get the same sort of differential equation. So I've written it, same sort of exterior derivative, but I've written it in real form here. And you just turn the handle and you find metrics. I'm not going to sort of define metrics with holonomy G2, but they're defined by a 3 form and closed. The 3 form has to be closed, and the 4 form, which that 3 form itself defines, because the 3 form determines the metric. The 4 form, namely star of the 3 form, that has to be closed as well. And those two, the closure of both those 3 forms is equivalent to saying that the 3 form is parallel, and therefore the holonomy reduces to G2. So you turn the handle in the same sort of way I did before, which Henrik asked me how I did, but I don't know how we did it this way, but it's more complicated. But anyway, this is the metric, one of the metrics you can get. You can get different metrics even from this single example. And the metric, I've written it down very explicitly, that's the 3 form. The 3 form, you can easily find what the orthonormal basis is. So you can put this 3 form in standard form with your powers of t weighting different elements of your original orthonormal basis to get the new orthonormal basis. And that's the metric you get, which is going to be Ricci flat. And even this I once checked on the computer, and it is Ricci flat, because these these one forms, they're very explicit. You know, the first four are just exact, they're just D of x1, x2, x3, x4. And then these other ones, they're very like sort of left invariant forms I wrote down before. To have a this is, you know, to my mind, possibly the simplest known, in terms of coordinates, this may be the simplest known metric with holonomy G2. Not complete, but it's sort of half complete, because when t goes to 0, we have problems because of this term here, but t can go to infinity. So that's an explicit example of a metric with holonomy G2, produced in the same sort of way. So, you know, if you want an introduction to metrics with special holonomy, it's, you know, one can understand them explicitly coming in the differential forms, the 3 forms and the 4 forms. You can understand them from these nil manifolds.
Simon?
Yes.
Is it obvious that the holonomy is exactly G2, or you just have to explicitly check?
Well, I think, you know, if it wasn't G2, it would be reducible, right? And you have to, it's sort of, it's fairly obvious, yes, that it's not reducible. I mean, this is an irreducible nil manifold. So, you know, the point is, this is, you know, it's an interval times a compact 6 manifold. So I think the answer to your question, honestly, is it's not obvious, but it would be easy to check that.
Yeah.
Okay.
Would you recommend a reference for this where this is probably most pedagogically explained?
A reference, I think probably my paper with, I mean, the most rigorous treatment of this, I think, is my paper with Vestislav Apostolov and Salomon. It's a unique paper in which we put this in a sort of more general context. Okay.
Thanks. It sounds like a great exam question. I'm just preparing some evil outcomes for this.
Okay, let me move on. So I mentioned nearly Kähler going back now. Nearly Kähler manifolds. We're now finished with nil manifolds. No more nil manifolds today. Nearly Kähler manifolds, I forget why I mentioned them, are examples of half-flat here, examples of half-flat manifolds. We're now going to talk a bit about nearly Kähler manifolds and a bit about the deeper work that other people have done in this direction. So again, as many of you know, there are 4 sort of homogeneous nearly Kähler 6 manifolds. There they are. We can more or less forget about the first one because so all of these, the cone metrics on these, any of these 4 have holonomy, a subgroup of G2 or possibly equal to G2. But the first one just gives the flat metric. Don't forget about that. The cone over S6, of course, gives the flat metric on R7. But these 3 here, before Spiro tells me, of course, they will give asks me, they'll give metrics with holonomy equal to G2, the cones over these 3. So, you know, the point is, I'm going to talk a bit about this example, but the other 2 have the advantage that these are both, these fiber over S4, this one fibers over S4, this fibers over CP2, and these are twistor spaces, so-called twistor spaces, a la Roger Penrose. Although the G2, because we're sort of talking about nearly Kähler, we have an almost complex structure, but it's the non-integral almost complex structure. So you can construct on a twistor space a non-integral almost complex structure, which is what we have really here. Huge striking development 3 or 4 years ago was the discovery by Lorenzo Foscolo and Mark Haskins that there are non-standard co-homogeneity 1 nearly Kähler metrics on S6 and S3 cross S3. So it's very surprising. It's also known that you can get smooth quotients. I don't know the others, but at least of S3 cross S3. And I don't think these have been completely classified, but there has been a partial classification by Schenter, Cortish, and Vasquez of these. And these are actually these smooth quotients, these by some finite group. These are sort of important in constructing new metrics with holonomy G2, but I'm not going to mention that today. And then a rather nice example, which is of current interest to physicists. You can actually, there's a natural Z2 action on the flag manifold, that sort of commutes with the SO3 inside SU3, and you can actually think of the quotient as the twistor space of CP2 factored out by complex conjugation, which itself can be identified with a sort of orbifold structure on S4. I'm not going to say more about that today, but this is an example of a singular. This is not a smooth quotient. This is an orbifold quotient because there will be fixed points of this Z2 action. Similarly, obviously here, there's an RP2, which is fixed by complex conjugation, and this becomes the Veronese surface in S4. So you have this sort of orbifold structure. But these will give rise to sort of singular G2 spaces and so on. So I just wanted to say a bit about how you can construct G2 metrics from S3 cross S3. And let's see if I can explain this. I'm going to try and explain it with a picture. But here's the text. So I should have, first of all, I didn't have time to sort of have pause functions in these slides, but just look at the first paragraph, first of all. So we know that the cone over a nearly Kähler manifold has holonomy G2, but it's well known, as sort of old work with Robert Grant, that these three conical metrics, that they can be smooth, they can be deformed into smooth complete metrics, which have an asymptotically conical. We can smooth out the vertex of the cone. So, for example, if you're talking about the, so if you do that for S3 cross S3, you, instead of the cone over S3 cross S3, you get the spin bundle over S3. And for the two twistor space examples, you get the bundle of anti-self dual 2 forms on over S4 or over CP2. And these have complete metrics well known with holonomy G2. These have been equal to G2, and these have been widely studied. And they're asymptotically conical, which is still a rather special sort of condition. Now, in terms of studying these three examples, most progress has really been made by the first one. That's the spin bundle over S3, or the one, let's say the one arising from S3 cross S3, the one containing the nearly Kähler manifold S3 cross S3. And it's now understood that this, by the work of different work now of Lorenzo Mark and Johannes Nordstrom, it's now understood that this very special asymptotically conical, I mean, I have to call it the Brandt-Salomon metric, otherwise the experts might know what I mean, but this well-known Brandt-Salomon metric, it's now understood that this is a sort of point inside a one parameter family. It's a sort of phase change point inside a one parameter family of metrics with holonomy G2, one side of which gives a family of complete metrics. And this works very well. This theory works because there's a co-homogeneity 1 action again by this group. In particular, there's a U1 action, which is very important. I'm going to show you a picture of this in a moment. But the message to take away is that this sort of old metric discovered years ago by myself and Robert fits in a one parameter family of metrics which have very different geometrical properties. Indeed, these metrics are what are called, apart from the R1, they have the so-called asymptotically locally conical structure, which means it's not a cone at infinity, but there's a sort of circle action with fixed size at infinity. And these were first sort of, their existence was first discovered really by physicists. And there are two families actually, B7 and D7 family. And the other part of this picture is that you can sort of understand these because they degenerate. If the circle size goes to 0, they sort of degenerate into asymptotically conical Calabi-Yau spaces. So my picture here to try and explain this is a schematic picture. These are not genuine curves. But can you see the curves is the first question, because I added these afterwards to the file. Can you see these black curves?
Yes.
Yes, okay. So this is a schematic picture of what I'm trying to say. And see if I can. I was trying to draw something. Yeah, okay. So what's going on here? So we're talking about, there are two aspects to this classification. One is we're talking about metrics of cohomogeneity 1. That enables us to represent such metrics by curves. So each curve represents a metric with holonomy G2 or some exceptional case. Each curve represents a metric which may or not be complete with holonomy G2 on some 7 manifold that contains S3 cross S3, I guess. The other aspect to this setup is that we have a circle action. That was the U1 I mentioned. And there are different ways this circle can act. So we're really, if you like, we're starting with the 7 manifold S3 cross R4. And the circle can either sort of act on the S3 giving the Hopf vibration, or it can act on the R4 given the map to lambda 2 minus. So, you know, if it acts on the S3, you get the picture below, but I'm really, the picture below will also have curves. It's just right the same as above, but I'm just telling you what's happening above, which corresponds to U1 acting on R4. And this U1 action, you can sort of, certain metrics, well, you can collapse this action and imagine that these U1 orbits become smaller and smaller, and in the limit you'll sort of get Calabi-Yau metrics. So you'll get asymptotically conical Calabi-Yau metrics, which these are these sort of dashed curves at the end. So in particular, you'll get an asymptotically conical Calabi-Yau metric here, which has one singular orbit, which is S3 cross R3. Similar thing below with the different singular orbit. And that corresponds, the one up top corresponds to the smoothing, I think, of the conifold, and the one below the small deformation of the conifold. That's the Calabi-Yau picture, which is on this extreme right-hand side of the diagram. Whereas these curves here, these are the Brandt-Salomon, these are the asymptotically conical standard metrics, Brandt-Salomon metrics. In fact, as a metric, they're both the same, but they're different U1 actions you can consider. In fact, they're really 3 in a certain sense, because there's a Z3 acting. So you think of this thing in 3-dimensional space, there's probably another curve going down the other side, but 2 are equivalent. So anyway, I'm just doing this one at the top. There's certainly U1 action. Now, all these curves here, they all represent complete metrics with holonomy G2, but they all have this, they have this asymptotically locally conical structure at infinity, which means that they're asymptotic to sort of this cone with this fixed circle at infinity. But you see, as you get closer and closer to the previously known Brandt-Salomon metric, you get this sort of picture, and you know it's a sort of thing you see in things on chaos theory. You get this sort of bifurcation. If you go beyond this, you get other metrics, but these are going to be incomplete metrics, actually. So you see, there's this sort of boundary situation here. And there are other metrics in this picture. There's a sort of, this metric here dotted here, this has a conically singular end and an asymptotically locally conical end, and so on. So that's don't have time to say any more, but that's the really quite exciting work that has gone on to further understand the metrics that are somehow related. Oh, by the way, I mentioned these families B7 and D7. So the B family would be here, I think, and the D family, if I got it right with that, of metrics would be given by curves below, like this one here. Okay, so you can read about that in the references I've mentioned. That's the situation for somehow arising from the first, the starting point was the nearly Kähler manifold S3 cross S3. Let's get rid of all this squiggle. Now, the rest of, now I've come to the sort of, in a sense, the last part of this talk, in which I want to do something slightly different, and it's in some sense it's less deep, it's more naive. I'm now going to pass on. So I've been talking about this nearly Kähler manifold S3 cross S3. Now I'm going to now move on to the next one in my list, which is CP3. So I'm now going to go back to the cone over CP3. So that's sort of easier. I'm not talking about the smooth metric. And I'm going to talk about the cone over CP3. So this has a conical metric with holonomy G2. And I want to think of CP3 as the twistor space of S4, CP3 fibers to S4. That gives it this natural or non-integral almost complex structure. And S4 can be thought of as sitting inside R5, but I want to actually reduce the symmetry group. The symmetry group of S4 is, of course, SO5, which is roughly the same as SP2. But I want to reduce that symmetry group to SO2 cross SO3 by simply splitting R5 as R2 plus R3. And if you do that, then that generates, in particular, I'm distinguishing a rotation of the force sphere. I'm rotating in the first two coordinates, if you like, and that gives me a U1 action that will also pass to a U1 action on complex projective 3 space, which, as I show in the next slide, you can think of as left multiplication by unit complex numbers on C4. And the question is, what can we say? I mean, following the sort of program of Attir and Witten, what can we say? Again, you see, we're talking about SO2 or U1 actions. So what I was saying before about these fancy curves, that was very related to the collapsing of circles and U1 actions. Here we're also looking at a U1 action. In a more naive way, we're looking at this U1 action on this cone. It's effectively on CP3, but therefore on the cone. And we want to sort of understand the geometry of this quotient. This is a 6 manifold. You know, earlier on in this talk, I was building metrics with holonomy G2 from hypersurfaces. Now I want to try and look at the quotient, the 6-dimensional quotient. So naively, you might think this should be Calabi-Yau, but of course it's not going to be Calabi-Yau because this has a reducible holonomy. The holonomy is equal to G2. It's not product of G2. It's not a product of SU3. So this won't be Calabi-Yau, but this should have some sort of features, this quotient. It should somehow have geometrical features which resemble Calabi-Yau with maybe Lagrangian or special Lagrangian submanifolds and so on. That was the idea of Attir and Witten. But we want to see whether this is true, to what extent it's true. So the aim is to study the quotient space of this 7 manifold by this rotation action, U1 action or SU2, this circle action, and see what we can say about the quotient. Well, the quotient, I'm going to have to speed up, but the quotient is, you can identify with R6, as I'll explain in a moment. And we have this residual action by SO3, and SO3 is just going to act diagonally on these two R3s. So that reduces everything to basic 3 vectors, you know, in undergraduate study of undergraduate vectors, you know, cross products, scalar products, but we just have 2 copies of R3 instead of 1. So you need 2 undergraduates to do this work instead of 1. So the next slide is technical. So I'm just explaining here, I won't go through the details, but I'm just explaining that this action by SO2 cross SO3, you can lift it to 2-dimensional quaternionic space, and you can think of it really as an action by SU2, by U1 on the left, and well, by U2 on the left. U2 on the left sitting inside SP2, which will commute with the right actions you use to define CP3 and S4. So this SO2 cross SO3, really, you can think of it as coming from a U2 acting on R8. But if you do that and you check what happens in complex coordinates, you actually see that R8 is split, not really as quaternionic space in the usual way in which I put the quaternion would consist of the first 2 complex numbers, but it's sort of, you actually, because if you look at the weights here, you're actually mapping, you're sort of identifying this one with this one, or in real coordinates, you're sort of matching somehow the real coordinates x0, x1, x4, and x5 are sort of put together. So you've actually split the R8 in a slightly different way as R4 plus R4, but you can think of those 2 R4s as sort of flat hypercalar spaces. And, you know, it's a bit like we did earlier on in the lecture. So we have these 2 hypercalar spaces, and that enables you to get moment maps to the corresponding omega 1, omega 2, and omega 3 correspond to these two spaces, but you have two of them, so you have two triples, and you can get a moment map to the two corresponding SU2s, which is R6. So there's a natural moment map in this setting. Because of this U1 action, you get a moment map to R6. So let me just say that on the next slide. I know time's getting on. So here it is explicitly. If you know about Gibbons-Hawking construction, this will be understandable. So I just get naturally, I'm just telling what it is, so you forget what I just said a minute ago. Here we have the cone over CP3. Here are four complex coordinates, if you like, four coordinates mod a circle. I've still got the R plus action, and I just map them to two 3 vectors. Remember, R6 is really R3 cross R3, and these are the two 3 vectors. These are the coordinates. They're the usual standard sort of moment maps, except that I've chosen bars here, but that's not incorrect, just a convention. So I have this map. So what I want to do is I want to, in the last couple of minutes or so, I want to use this R6 to understand the geometry of this cone, which has a metric with holonomy G2. And a key function that's important is capital R, which corresponds to the radius squared on R8, but it translates into little u plus little v, where little u is the norm of vector u and little v is the norm of vector v. So these are not smooth in the sort of uv coordinates, but this function comes into it. Well, what can I do here to save time? So there's the idea of the twistor space. So this is just really just look at the top half of the picture. And we want to understand the geometry of this cone, and we're using the twistor space. On the other hand, we're sort of the twistor space S4 is the base, that's in R5, complexify R5, and you get round here and you get down to R6. That's basically the idea. The other idea is that the action that I talked about distinguishes two totally geodesic spheres inside S4, a circle and an S2, and it distinguishes a function S. Okay, I'm going to skip that actually, so you can relate these sort of bivectors, as they're called, the U and the V, to quadrics, not necessarily holomorphic in CP3. Then let me just finish by talking about co-associative submanifolds, because this overlaps with work of Spiro Karagiannis and Jason Lotte. That's a good thing to talk about. So we have this conical metric on the cone over CP3, and because of the way I started with R8, it's very easy to say what the 3 form is, the G2 3 form. It's just D of this 2 form, which is just comes straight out of the group action I was talking about. Of course, it's exact because there's no cohomology here. There's no 3-dimensional cohomology. We have this exact 3 form. And that means that when you pull this 3 form back to any orbit by SO3, for example, the SO3 I was talking about, the pullback of that 3 form will be 0. It follows that you do expect to be able to find co-associative submanifolds, which is one of the quests. You want to find co-associative submanifolds. These are 4-dimensional, sort of calibrated by the G2 4 form inside a manifold with holonomy G2. You want to find those. And in this sort of situation, when you have an action of SO3, you expect to find them as unions of SO3 orbits. So that's the idea. I know Spiro and Jason have done this in a different way, but let me, for all the Salomon metrics, but let me just do it, explain that this will be my last slide, explain what happens for the case of the cone over CP3. So again, it's a bit technical, but let me just explain what's going on. So we have this cone over CP3. I've explained to you that the best coordinates to use are by taking the quotient to R6. Now that's a circle bundle. So we have an angle, which is the angle around the circle. So that will remain as an invariant because that commutes with SO3, the SO2, that's the SO2 angle that commutes with SO3. But then once you go to R6, you've got vector, an element of R6 is this so-called bivector. SO3 is acting diagonally. So the invariants are the norm U, the norm V, and the scalar product U dot V, because SO3 is acting diagonally, so it preserves this. So these four functions will determine, if you set them constant, they'll determine an SO3 orbit in this manifold. This is a 7 manifold, so you'll determine a 3-dimensional SO3 orbit. On the other hand, we're looking for co-associatives, which will be unions of such orbits. And everything's invariant by SO2, so the theta will remain as to distinguish one of these co-associatives, but we're looking for only 2 invariants rather than 3. And the 2 invariants that work are these 2 quantities, A and B. Just these simple combinations of these invariants. Of course, little u squared is just vector u dot vector u. So everything comes from these vectors u and v. And these 2 invariants, together with the angle theta, will distinguish a co-associative submanifold of this cone. And I've tried to draw the picture here. The idea is this, that there are special orbits. In fact, there are really 2 components of these co-associatives, but a generic co-associative is really, these blue spheres are twistor fibers in CP3, but because we're in the cone, we've crossed with R+, they can have different sizes. And a given co-associative, this yellow thing is a given co-associative, it will intersect these spheres in small circles, parallels of latitude of different height. And this height will get higher and higher, or lower and lower, and at a certain point it will become a pole and it will die. So the co-associative won't actually get to the end, which is the circle. It won't, there are 2 ends of S4 in a sense, the circle one end and S2 the other end. And it looks as if it's singular. That's just because I've drawn the circles horizontal and not vertical. Had I drawn the circles vertically, you'd get something that looked roughly like a paraboloid and it would be smooth. So that's the theorem. I just wanted to explain that all this explicit stuff can be used to do that. I'm not going to show you any more slides. I've run out of time. I was going to say something about use symplectic structure on R6, but if the slides will be available, I'll look at that.
Thank you. Have we got any questions for Professor Salomon? Comments? Maybe I'll begin.
Yeah.
Have we done, any gauge theory on those families of metrics? Have we thought about how to maybe distinguish some of them from a gauge theory perspective, some expected behavior of the moduli space?
Henrik, you're the expert on this. I think there has been work by some people on this, but if you're talking about G2 instantons,
yes,
they're difficult to find. I think, maybe Spira knows something about this. I think Jason has done work on G2 instantons, or he has this deformed version. And I think there has been work. I don't know the results myself. So I think the answer is yes, but probably only on the asymptotically conical metrics, not on these more general metrics, is my understanding, but I'm not really up to date.
So might be worth pursuing, right? Trying to differentiate these in terms of what's expected from the
maybe
moduli
Gonzalez knows something about that. I don't. In theory, yes, but I think in practice it's going to be pretty hard because they're difficult to pin down in any case, these different metrics.
The ALC ones are not explicit, right? Mark and Lorenzo.
Sorry.
Yeah, they're just, they're solutions of some dynamical system, but they're not, they're not, they're probably more explicit than, say, Calabi-Yau metrics, but they're not. not much one can say. I mean, that doesn't mean one couldn't get results about instantons, because you can do some explicit results concerning these more general metrics. I think you can get some results concerning these more general metrics, but whether that extends to instantons, I don't know.
Yeah. So it's not related to this vibration by co-associatives or anything, but on R3 times S3, there are all these G2 holonomy metrics with different behaviors, asymptotically conical, which is the Brian-Salomon one. And then one of these ALC ones is the one constructed by 4 physicists, Brandhuber, Gukov, Gomes, and I forgot who was the other one. But on those, Jason and I constructed G2 instantons. And we found the 1-parameter family of G2 instantons on the Brian-Salomon one, which is the same that Andrew Clark. Andrew Clark was the first one to find those.
Yes.
And then on the other one, we found that there is a 2-parameter family.
So you're saying you have found instantons on these more general ALC ones. Okay.
Yes, on the ALC one.
Okay.
On the ALC ones, there are more.
And you can distinguish therefore from what you just said a second ago. You can distinguish the ALC ones from the AC ones.
Yes, using just instantons with the same symmetry group, they are different in both metrics. And we can also say something about the holonomy of them along the circle at infinity with finite length and things like that.
Right.
That's it. That's in your paper with Jason, right? The one with
yes, one of the papers Jason and I have.
Of course, I mean, I should add for non-experts, when you have one of these G2 spaces, I mean, ideally we'd like to do this for compact G2 manifolds, but that's almost out of reach at present. I mean, there are 2 dual problems. One is to construct these calibrated submanifolds, whether they be associative 3-dimensional or co-associative 4-dimensional. That's one problem. And the other problem is to understand instantons, special connections on bundles over these manifolds. And I guess the 2 problems are sort of there are interactions between the 2 problems.
Yes.
And so the cheap thing is to try and do it with these complete metrics, where everything's explicit, and that's, I suppose, where you try and start, because the hope is that these complete metrics can be used to sort of glue in something and get eventually get some sort of compact example.
Okay. Any more comments or questions?
Who has the dog as their emblem?
It's Andrew.
Oh, that's Andrew. Does a dog have a question? Sometimes they do.
The dog was quite satisfied. He understood everything.
They're very inquisitive eyes.
Cats. Cats ask questions.
Oh, the cat.
No.
The cat. Your cat.
Right next to each other.
Think and don't speak.
Ray solved this.